Welcome to the third and final part of our three-part installment on Fourier transforms. In this lesson, we'll go through an example discrete Fourier transform. The best way to really understand how the discrete Fourier transform operates on your data is to go through an example. So here we have a basic sinusoid with a frequency of 1 hertz. So this will result then in a period of 1 second, so frequency of 1 hertz, giving me a period of 1 second. And based on my amplitude here, I'm going from a minimum of -1 to a maximum of +1. I could write a description of this signal with respect to time as little y of t is equal to 1 times sine of 2 pi t. Let's sample this signal with a sampling frequency of 8 hertz, and let's take a total of capital N equals 8 samples. So I'm effectively sampling a single cycle of this sinusoid. So in red here, I'm showing each of these samples, and we could come up with values for each of these samples. For example, my first sample, x sub 0, that'll be equal to 0. And my next sample, x sub 1, that'll be equal to 0.707. X sub 2 is equal to 1, and I'll continue all the way up to x sub 7, which will be equal to minus 0.707. So all of these notations I've listed here in red, I need this information to accurately compute the Fourier transform. I need the sample data at each moment in time, and I need to know how many samples I've taken altogether. So here I have capital N is equal to 8 samples in total. Let's start with the capital X sub 0 term. I'm looking at the 0th frequency bin. So I'm going to use all of the information from my sampling and my complex exponential here to evaluate the frequency content in this 0th bin. So right off the bat, let's take note of something. This k term here, this is going to be equal to 0. And so if I have a little k equals 0 here, well, I'm taking the exponential of 0. So as a result, this whole complex exponential, well, this is going to be equal to 1. And so x0, that's going to be equal to the sum of all of my samples. And if I add all of these values here, well, I'll find that that summation is equal to 0. So as a result, my capital X sub 0 term, that'll be equal to 0. What that's telling me then is in this 0th frequency bin, well, there's no frequency content in that original signal related to this 0th bin. And since our signal was a 1 hertz sine wave, we're not expecting any DC component to that. Now the x1 term, that's a little bit more interesting. Let's write the sum here, and let's start with the x0 term. We'll multiply that by e to the minus j times 2 pi times k, which in this case will be 1, times n, which will be 0, and we'll divide that by capital N, the number of samples, so that'll be 8. And we'll add to that x1 times e to the minus j 2 pi times 1, now times an n, which is going to be 1 divided by 8, and so on and so forth. And what I can do is go ahead and substitute for all of these x0, x1, x2 type of terms. I can substitute in the numerical values of my sample data. And so with this setup, I can now perform the Euler expansion. So I can now write out x1 as 0 plus 0.707, and now we'll perform the Euler expansion. That'll be 0.707 times cosine of minus pi over 4 plus j times sine of minus pi over 4. And so we can solve for some of these numbers, and we can write x1 equals 0 plus 1/2 plus j times minus 1/2 plus a minus j, and so on. And let's recall then exactly what these samples are referring to. So my 0, that's a result of my x sub 0 term. This 1/2 plus j times minus 1/2, that's a direct result of our x1 term. And this minus j is a direct result of our x2 term. And if we total everything up, what we find is that our x1 term is equal to 0 minus a 4j. So my first frequency bin has a complex coefficient of 0 minus 4j. And we can do the exact same thing for x2. So let's do that here quickly. So here I've written out my sum again. So I have x2 is equal to 0. That'll be times e to the 0. In this case, n will be equal to 0. Plus 0.707 times e to the minus j times 2 pi plus 2, k is equal to 2 now, and times 1. So n is equal to 1, and that's divided by 8. And once again, I've applied Euler's formula to describe x2 in terms of cosines and sines. And I can evaluate each of these terms as well. So here's all of the requisite terms as well as the original components of the signal with which they are responsible. And I see right off the bat that several of these terms will cancel out. So here's minus 0.707j plus a 0.707j, so those will cancel. And so I end up with my x2 term equal to 0. So as a result, my second frequency bin, that's going to be equal to 0, which means there is no content at that frequency. And this makes sense, right? We had a 1 Hz sine wave, so we're not expecting any content at this frequency. So here I've calculated all of my Fourier coefficients, and I want to plot an amplitude spectrum to give me some idea of the frequency content in my signal. So note here, I have the same number of frequency bins as I do number of samples. So I have 8 bins, given that I had capital N equals 8 samples. And so the resolution of my frequency bins, my delta F, is going to be my sampling frequency, F sub s, divided by the number of samples, capital N. And so in this case, I had 8 Hertz divided by 8 samples, so that gives me a delta F of 1 Hertz. So let's look at our coefficients on the x-axis of this frequency spectrum. I have my coefficients x0 through x7. And so based on my delta F, I'll have an x sub 0 at 0 Hertz, I'll have an x sub 1 at 1 Hertz, x sub 2 at 2 Hertz, and so on. And once again, note that this is not a continuous frequency axis. This is a discrete frequency axis. So the next step then is to take a look at the magnitude. So the magnitude of these samples is rather mundane. However, the magnitude of x1, that's going to be 4, and the magnitude of x7, that's going to be 4 as well. So if I plot these amplitudes on my amplitude spectrum plot, I'll find that at x1 and x7, I have an amplitude of 4, and at x0 and x2 through x6, I have an amplitude of 0. And this makes some relative intuitive sense because I started with a 1 Hertz sine wave, and in my 1 Hertz bin, I have frequency content. However, I also have something other than 0 in my 7 Hertz bin. And this is because this is what's referred to as a two-sided frequency plot. And ultimately, the challenge is that I have that Nyquist limit based on my sampling rate. So if I'm sampling at, let's say, 8 Hertz, I'm not going to have any frequency content showing up in my signal above 4 Hertz. So what I need to do then is effectively fold my frequency plot here and add. So at 4 Hertz, that's my Nyquist frequency. If I'm sampling at 8 Hertz, my Nyquist frequency is always my sampling frequency divided by 2. So my Nyquist frequency is shown here as 4 Hertz. So I'm going to fold this plot, this amplitude spectrum plot, about that 4 Hertz line and add those two amplitudes together. So when I perform this folding, my 1 Hertz bin now goes from an amplitude of 4 to an amplitude of 8, and my 7 Hertz bin is now 0. So now all of my bins are 0 except for my 1 Hertz bin. However, the amplitude of our sine wave that we started with, it was not an amplitude of 8, it was an amplitude of 1. So what's going on there? Well, what we have to do here is divide all these amplitudes by 8 to get the true amplitude here. So if I divide everything by my number of samples, what I end up getting is 8 divided by capital N is 8, so 8 divided by 8 is 1. And thus I end up with an amplitude of 1, which is what I'm expecting given the 1 Hertz signal with an amplitude of 1 that I created from the beginning. So ultimately then, I'm ending up with a signal with a frequency content at 1 Hertz and an amplitude of 1, which is good because that's what we expect. So what I end up with in the end is a single non-zero coefficient. So on my real and imaginary axis, I end up with a vector with a magnitude of 1. If you recall, I had to divide 8 by capital N, so 8 divided by 8 is 1. And if I measure my angle, if I measure from the positive real axis going, say, counterclockwise, I'll end up with an angle of 3 pi over 2. Or I could measure it in the clockwise direction, and that would be an angle of minus pi over 2. So what this is ultimately telling me in the end is that this vector on the imaginary plane is going to correspond to a cosine function described by x of t is equal to 1, a magnitude of 1, times the cosine of 2 pi times 1, we had a 1 hertz frequency, times pi minus pi over 2. Well, a cosine with a phase of minus pi over 2, that's effectively a sine wave. So what I end up with is something that looks like this. We have a sine wave with a period of 1 second, given the frequency of 1 hertz, and a magnitude, an amplitude of plus or minus 1. So we go from our 0 line up to plus 1, from the 0 line down to minus 1. And so this is the reconstruction where we've effectively gone from these frequency coefficients, and via the inverse Laplace transform, we've brought this signal in the frequency domain back into the time domain.